Hey humans, I'm Aaron Rosenman, and with my full-time job, I'm the Director of Security for Research and Development for Pluralsight, and part-time I work for the Air Force in Defensive and Cyber Operations. And welcome to my talk on ransomware creation, detection, and response. Now, what do I mean by that? What do we expect from this? Well, I'm going to walk through what it's like to create ransomware as the author of some malware that I made for training that was actually leaked out. And that gives me a bit of a unique perspective to then talk about some of the lessons learned from that creation and those detections that were done by different antiviruses and some things I was able to pull from those detections. And then after that, after we find out how those detections imply ways to then invade those antiviruses once again, we'll talk about what you can do for incident response to ransomware. And the whole purpose of this before we start is to make sure that you understand the engineering and practices and malware detection response capabilities, but also so that you understand that you don't have as much of a false sense of security, which is another theme from all the research that I've been doing, whether it's air gaps or whether it's antivirus. I don't want you to feel like you're safe if you're not. And before we continue, please make sure that if you have any questions, feel free to chat in them. We're remote this time, thanks to COVID. So go ahead and put those in the chat and I'll answer them throughout the presentation. So I know you're probably reeling from when I said I created ransomware. That sounds really bad. It's not anything that can actually be harmful. It can't be paid, but let's talk about how that happened. So I really, I guess, took really far the know your enemy, become your enemy situation. And I wanted to understand what all of the requirements for ransomware. And so for a training event where I wanted to make a really realistic simulation, I made some malware. It was in a contained environment, and one of the students released it, even though there was an NDA saying that they should not. And when it did get released, it just went on Twitter and like everybody took it over, and it ended up getting uploaded everywhere. And this picture is actually from Malpedia, who did some reversing on it and called it IronCat. I wrote a blog about how it works. You can go to my website and find that if you want. Now, so this ransomware gets released, and the very first thing is it goes on Twitter, and of course, Malware Hunter team got a hold of it and starts reversing it, saying, "Oh no, did REvil or Sodinokibi, did they go to Golang? Because I used Golang to make this malware." Okay, and then it kind of spread around, and different people. This is translated from Russian. This is Malpedia picking up. There's the picture that we got because of the note that was dropped. It was called IronCat because it had different strings in it that related to IronCat, which occasionally is my hacker handle online. And then, of course, the different software companies that will profit off these sort of things started releasing things saying that they could clean your device of ransomware, which I thought was excellent because if you look through it, there's no way to fix this once you get hit. And so this lets you know that every single one of these companies, while also saying that I by myself was this advanced criminal actor organization with like advanced evasive capabilities, is also kind of not really telling you the truth when they say that they can fix this problem for you. So that was kind of a really neat perspective to get as well. And finally, what happened is Microsoft named a whole malware family after that. And so that exists, and we'll see this again later. And then eventually everybody figured out, hey, this is not actually REvil or Sodinokibi. It's actually just someone spoofing it. And the reason they thought I was spoofing it is because I used a previous ransomware response note. I kind of neutered it and took the capability to pay out of it and a lot of the different language that was in there for being able to go to the site and like pay Bitcoin and that kind of thing. But a lot of the note was still the same. So that's why they thought it was the same. But when they looking through it and obviously reversing it here, they're finding all these IronCat strings because of the way that it operated. And what I just talked about is, what I wanted to understand is, do you feel safe? Do you feel safe because all these different groups picked this up and immediately antivirus companies, and we had detection and all this stuff that made it like, okay, when ransomware gets out, detections are ready and the consumer's protected and enterprises are protected. But my real question is, was that really true? And that's what this talks about is that true? And what are those detecting on? Is the detection actually correct? Or is it even really effective at all? Like, is there ways to bypass the detection that are really, really easy for adversaries? I didn't know, and that's what we're going to kind of figure out as we walk through this. And to really understand, we want to start with what was the IronCat ransomware? What did it do? Okay, so actions taken by this exe. The first thing was that, really based off the way I wanted to be able to use it for the training environment, I set it up so it used arguments. So when you run it, you had to put in, what mode you wanted to run in, whether it's encrypt or decrypt, and then the key that you wanted to use to encrypt the data. And so this ended up being something interesting because it made it harder to reverse, and we'll see that later too. But every time you didn't put in the correct argument or ran it with no arguments or put in the wrong argument, it would give you kind of a different message. So you can see the beep boop here with the error. You can see the cheeseburger situation and I'm Iron Cat, you're not. So that's why it was called Iron Cat. And the main actions that this thing took were to use ANS to encrypt the files. It dropped the payload called Pay the Piper, which was that kind of spoofed note. And then at the very end, after encrypting those files, it dropped 4 batch files into the C Windows folder. The first one was a SFC backdoor, and then it ran a batch file to create a registry backdoor using utilman, and then deleted the volume shadow copies like normal ransomware would, and then clears all the events logs. Now, before all that could happen, it also, the simulate real ransomware and have network traffic, sent out a packet to what was at the time an in-range domain only called Fakebook, simulated Facebook. And it was a red herring IP and the header, and also like some different UTF characters. I think there were Chinese characters, just to kind of throw off people for attribution as well. So that's what it did. It had a base64 encoded password that was sent in that packet. So hopefully if you found the packet, you could then decrypt your malware. That was the whole point. Now, when this was uploaded, it started to spread around in VirusTotal. In the top right, you can see there were multiple different files. So for this specific training event, we had one that hit a specific file in programs. It was initpub, which is for www-data for websites on IIS, whether it was the user's file and different kinds of user files. And each one of these that was uploaded, I then uploaded all of them myself afterwards also, so that they would be detected, kind of had something slightly different about them. And so really the only main thing is exactly the same code. The only thing that was really different was the path that it went to encrypt. And so here we can see it matches a rule for QNAP, which is interesting, like why is it making that match, and just some of the paths that it found. And we have that someone else reporting that it's Snatch ransomware, and Intezer picked it up in this Thor Yara rule. And as we go through, this is a different file, and this one had 39 out of 69 detections. Intezer again, Thor again, same thing with the Snatch malware, and then like slightly different reports on what actually ran. And now when we go to the SQL version, so this is trying to hit an SQL server, it was 38 instead of 39. So that's one less rule with the exact same code. So who's missing what, right? Like that's what I started to want to understand. Also in this one, there was no automated signatures. So though this was uploaded around the same time, there were no Yara signatures for this one specifically, and I wanted to know why. Next, we have the same results, but this one does have the Thor APT scanner picking it up. And for whatever reason, for this specific sample, it detected that there was a registry add for the debugger backdoor, but only on this one, even though that code existed in all of them. And then again, I took the original file, changed it to just .hta. I didn't actually change the code, and all of a sudden I have more detections. And instead of QNAP, it's Yomi Hunter. And I have no idea why, but what that tells me, just inference, is saying just the name of the file generates a different kind of analysis and is used in the detection of malware. So that was like an interesting hint for how these detections are done by the different engines. And so when we look at IAA users HTA, sure enough, Microsoft still had this as Iron Cat. So that's a pretty good detection, but many others had it as something completely different than they had it previously. And so, okay, there's all these different files, but let's talk about the anatomy of ransomware. How should detections be done if we just think about what the requirements are for making ransomware in the first place? Well, you want to target a specific set of files, ideally files that are important to the user, to the organization, because you want to properly perform your business, right? You're going to open, change those files, and you're going to resave them like over and over and over rapidly. And it probably requires admin access unless you only need user access just to get to that specific user profile. If that's okay, then fine, but ideally it has admin access. The next part is it drops backdoors. Generally, that's so the actor can get back in and continue access, whether that's after the ransom paid or during. Sometimes I've seen them mess up and have to get back in. And that's not a 100% requirement. It doesn't have to be. But then the next piece is you really want to delete backups, delete volume shadow copies so the victim can't recover, and delete the Windows event logs, just kind of cover your tracks, because why not while you're there? Also, you need to get a key back that is associated with that deployment of ransomware, so that when the customer hopefully pays, you can use that key to unlock those files for them to continue your business practice, depending on who the organization is and what their actual intent is. But that's kind of another requirement. Also, you can't break the system. So knowing that all of those things have to happen, we didn't really see that in any of the analysis. But why? Like, what did it miss? Well, it didn't see the batch drop of the files. It didn't see the event logs that were deleted, VSS copies deleted, C2 domains for the DNS request. It didn't catch that, or at least say what DNS requests were made. There's no mention of like keys being in the packet, even from the people who did manual analysis, nor the CEFC backdoor. And the file extension was initially missed as well. Like if you saw the reports before my blog came out, they didn't catch it. It said .encrypted is actually kind of using different ransomware groups saying this is the file that's dropped, even though it wasn't true, which is also just really interesting. And why? Why was it all missed? Well, if I go back and think about it, adding the arguments as a requirement really made it where when it tried to run in the sandbox, it couldn't, because those arguments weren't provided. So instead, you just get these sandboxes getting silly messages from IronCAT and no real execution happened. So kind of by accident, this was a defense evasion or sandbox evasion method. So that's one interesting finding. And also, a lot of this is focused only on static binary analysis, and Golang is kind of difficult to analyze for now. It depends who you talk to, but it's just different looking than like a C++ program that's been compiled. So, okay, that's all of the kind of characteristics of what happened with its creation and some of the static analysis. But let's talk about detection, like what was good in the detection that made sense. Well, one thing that was good is kind of as time went on, these samples are analyzed, and Intezer found that it was unique code. So when they looked at code and used fuzzy hashes to understand what code was being used. Now, again, it was interesting because that doesn't actually match any of the hashes of any of the files that I had. So I don't know who uploaded this or what it was specifically, but it still seemed to match in like what it did and with the name tags and stuff. And so it was saying it was unique code, which is accurate. I did make all of it from scratch myself, and it did properly recognize it as Golang, where when you look at VirusTotal's report, it thought it was .NET for some reason. Now, Joe Sandbox really did detect that there was a Tor address in the text file, which tells me a lot of this analysis is being done based on clear strings in the binary. And then beyond that, I was just saying, hey, the biggest reason we think this is bad is signatures, because other people found signatures and said it was bad. Right, that's the top thing on there. So, okay, maybe remove the Tor file. We don't have to worry about it. Now, Malware Bazaar did actually categorize this as SoNoKibi. And that's interesting because, again, it's being categorized that way because of that spoofed ransomware node. Now, they also got IronCAT after a while because of the changes. But this all tells me maybe things that these antiviruses are looking at as tells for detections. And then finally, Yara signatures were created that I was able to download, and we'll be able to test those out and see what they were doing also. So based on all that information, what were these detections? Well, there was an automatically generated Yara signature, probably the ransom note strings, definitely the Tor address. One thing detected that there was a registry ad, so that's something to consider. Batch file execution probably should have been a detection, but I didn't see it anywhere. So that's something to keep in mind for if I want to try to make this evasive. And in my mind, what you should detect on is probably concurrent access to files, like very quick access to files by some binary, especially an unsigned binary, right? And so now the thing that I want to do is what's the least amount of change I can make to then evade these antiviruses. So I'm going to make small changes in this demo that's about to come up. I'm going to make small changes, and then we're going to see what the reaction is. So I'm going to change function names. We're going to look at a custom ransom note. I need to remove that Tor address. Probably will end up having to remove the registry ad. And then if I want to use a different backdoor, here's an option. And if I really have to, off they get to the behavioral analysis. So let's check that out. Now, those evasion ideas are just a hypothesis. Now, let's take a look at how this actually plays out. Keep in mind, the idea here is that based on the variations in the detection that I just went over, what are the least amount of changes that I can make to completely evade Windows Defender, the Yara signature, and VirusTotal. That's my goal. So first up, I want you to see what I'm working with. It's the same original files. So here's the MD5 for the IAI users.exe. IAI here stands for IronCat, of course, or I am IronCat. And here's the original MD5 for the variation that encrypts just a specific different folder. Now those are the same MD5s that you saw in VirusTotal, and you can also see here. And this MD5 has 52 out of 70 detections, and then the one for the file location in a different area has 38 out of 69 detections on VirusTotal. Well, last but not least, the Yara signature. And I'm not really sure how much effort this is. It does say it was automated, but then when I look at it, it has a user called Florian Roth, but I'm pretty sure he just made the automation. But you could look at automation as being a really heavy tool in itself. But either way, here's the original Yara signature, and it's highly effective against all of the original samples that are in this folder. So that means at the very least that the different names and different hashes and different target files aren't throwing the Yara signature off that scent. So it seems like that was a pretty good job. And a quick look at that signature file shows that there's 9 detection sequences, with the criterion for detection being that 7 of them are matched. And the file has to also be smaller than a specific size, which brings to mind another point, like maybe I just need to make really hefty sized malware and not worry about detection evasion, but that's probably a different talk completely. Next for the test machine, and rest assured, there is no tomfoolery or hijinks going on here. It's a fully patched Windows 10 with fully updated signatures. When I drop the known malware on the desktop, it's instantly detected and removed, and here we have a lovely IronCat malware family alert. So great, seems like we're super safe and Microsoft's on top of it. Well, when you look at many of those detections that we just talked about earlier, it seems like a lot of them alerted on Sodinokibi. Probably based on the copied ransom note from an incident response that I did to an RE-Evil incident. So maybe based on that conclusion or what I'm seeing there with those detections, if I change the ransom note, that will at least throw off these detections a little bit. So here I changed the ransom note to say even more things that an IronCat would say. And it's completely happenstance that cats don't have very good written English either. And it has nothing to do with my terrible typing skills and occasional issues with attention to grammatical and spelling accuracy. In general, this is not completely different from the original file on the left, with exception to this ransom note. Now I recompile this into IAI as back v1, and it's time to test out on the sweet Windows Defender detection capabilities. And to prove that this isn't a box of mirrors, you can first see the threat detection from the previous file. Then check out that real-time protection is on, as well as cloud protection. And I did not turn on the sampled submission here because I don't want this to get burned before I even finish the demo. So now I'm copying the new malware onto the desktop, and well, there's no detection. But that's okay. Evading these hash-based detections are one thing, but surely there's no way that this will be allowed to run, right? I mean, it's just the exact same code with a different message from a cat. Well, let's find out. Here on the desktop, I set up to run the executable with required command arguments. And, well, of course, this wouldn't be a live demo without a few mistakes. I'm just trying to make sure this is realistic for you. One requirement for the IronCat sample to run is for it to be able to resolve and send the HTTP packet to fakebook.com. Okay, so this seems like I forgot to enable the Hyper-V adapter. No biggie. Enabling that, I give it another shot, and it also means that cloud protection is also fully enabled. Still no detections, and then here we go to run it. And oh, there's a pop-up there. Oh no, that's not Windows Defender. It's just letting you know in a friendly way that files are waiting in a queue. Files waiting in a queue to be encrypted, of course. But there's still time, and as it finishes encrypting, now we see an alert. But it seems like it actually ran quite a bit there before that alert happened. So using the get np threat command, you can see that this is actually a different alert from the original IronCat alert. Instead, this is a behavioral alert. That seems like it's something that's going to be more difficult to get past than just changing the hash. So it seems like we have execution, and when I take a look at these sample files, I see that the note did drop, and the text of this document here was indeed encrypted. All right, I'm gonna exit out of that. And when you exit out of this window, there's all the telltale signs of ransomware execution. The desktop image is different, and links are broken, and there's notes left in every folder. And that by itself is interesting. This is saying that an up-to-date Windows Defender is essentially only checking the contents of the ransom note in the strings of the binary for detection. And if you change that, well, now at least I have execution on the box. It may actually get detected, but it's a little late because the ransomware already kind of happened. But I want more than that. I don't want to just trick Defender. I don't want this to be detected at all. And it should be more of a challenge to get past these behavioral detections, right? Well, now it's time for version 2. So what do I change now? Well, going over what I know, I realized that this is string-based detection. And so I'm going to go ahead and change significantly unique strings that occur elsewhere in the binary. And it also seemed to have issues with access to the NT-user file. And when I look at the name of the behavioral alert, it was called Accessibility Elevation F. Well, one of those batch files that's dropped changes the sethc executable, which is the binary in Windows System 32 that's associated with accessibility features. So that's fine. I may not be able to use that backdoor, but I can use a different backdoor later. For now, I'll just remove that as a function, because even if all I do is achieve ransomware execution, that's still the in-game goal. And one last touch. I noticed that some of the manual reverse engineers found absolute paths reflecting the folder structure I used when creating the project. This time, I'm going to use the -trim path option when I compile to make the path strings relative instead. But before I go straight to the Windows detection, I wanted to check on the Yara signature detection. So first I'm going to go back to version 1 and check to see that, yeah, the Yara signature is still hitting 7 of the 9 sequences, which was really the cap. So we got rid of 2 of the sequences. And honestly, if you think about what just happened, that's saying that this Yara signature that was generated is doing a better job than a fully patched Windows Defender signatures. But now when I test the version 2 that I just compiled, changing all those other unique strings, we get nothing. 0 detections. Which honestly was much easier than I expected. So now that I have the box checked for Yara signature evasion, I need to test Windows with these changes and see if I got past that behavioral detection as well. So I reverted this device back, I'm using Hyper-V, and now run the second version. And of course, again, I forgot to turn off the external networking, but this at least shows, after I get it working, that my addition of error strings for the HTTP error is also working. So there was some change to the code there as well. Now this time it runs, and guess what? Big reveal! 0 detections. No IronCat detection, and no additional behavior detections with full run through. One last test is VirusTotal. And surely with its sandbox execution and nearly 70 engines, it's not going to be as easy as just changing some clear text strings that happen to occur in the binary. Well, almost. With version 2, I now only get 12 detections from groups like FireEye recognizing this as snatch ransomware, which I saw before in the original detections. Now this got me thinking, what's my baseline? I wanted something to test that was really innocuous, that really wasn't malicious, so I made a Hello World application, and I dropped that into VirusTotal as well, and sure enough, 4 of the engines detected the Hello World app as malicious also. So that's really the best I can do, 4 or less. And we're saying that those 4 basically think that everything's malicious. If I get to 4 or less and it's these 4 players, I'll be happy with that, because I'm then getting past the major players like ESET and FireEye and Bitdefender. Okay, but before getting into some of the behavioral modifications that I think I might have to make based on the slide that I presented previously, I had one last idea. Developers are often told that they should use descriptive names for functions, and I think that probably applies for malware developers as well. And I don't disagree normally, but what about if I don't do that? I mean, if you're creating ransomware and the function name is encrypt or ransom note, that seems a bit on the nose, doesn't it? So to test this out, I changed function names and other strings that say ransom or the word crypt to friendly no or like entropy. And the last thing I wanted to do, there was still some function code for the registry utilman backdoor that was also dropped. Though it wasn't used, I think it was still in the binary. So I wanted to remove that as well. And after those changes, the code still does exactly the same thing. It still deletes the volume shadow copies, it still deletes all the logs, and it encrypts everything. So now it's the big moment. It's time. This is the end of this demo. It's time to hold your breath. If we were doing this in person, I'd be really, really nervous and considering whether or not I should have done a live demo in the first place. And though as this is loading, SecureAge Apex instantly decided that this was malicious. I'm pretty sure it just thinks that because it's a binary that's not Microsoft, it's malicious. For reference, Calculator, when you open it up in like Process Explorer, has 1 detection on virus total. So I'm not super upset about that. But by the time this is done processing, 0 other engines detected the sample. Not FireEye, not ESET, not Bitdefender, not any of them. This sample that all I did was change strings. It's just as effective as the original, and all I had to do was what basically constituted string replacement and remove code for batch files or backdoor tactics that are like 10 years old. I'm sure if I replaced them with something that was newer or more obfuscated, we would be able to get by with that as well. In fact, I can avoid dropping batch files completely and just do it all of it through the binary. And just like that, IronCAT's back. Okay, so I don't feel really safe anymore after I went through this and created all of that. What I actually feel is that maybe my antivirus isn't protecting me like I thought it was. Now, this isn't accounting for having something like advanced threat protection or in-game actually installed on a device. I didn't have that software, but for the average consumer, for the average enterprise user, being able to just change a few strings as a malware author and redistribute really completely bypasses that entire industry of appliances. And that's kind of concerning. But what it does do is it places a really high importance on better behavioral detection. So when I talk about that, it's EDR solutions, it's centralized logging. That password that was input with that argument would have been caught if all of the arguments and all of the commands that were ran in a terminal were passed back to centralized logging. They wouldn't have been deleted. We want to do that log analysis on Windows devices, and we have to be able to chain processes and track like file execution, that sort of thing. On the network side, J3 hashes would have caught the weird signature for the network traffic leaving the binary before it had executed. There's certificate anomalies, like the fact that this one didn't even have a certificate, as well as full packet capture would have helped us understand what that base64 string was doing, and we would have been able to catch that. Now, that's not necessarily how real ransomware works, but there needs to be a heavier focus on these things. It seems like antivirus shouldn't provide us the sense of safety any longer. So now let's talk about response. I don't want to provide all that capability, and I purposely didn't show a ton of the source code and won't provide that because I don't want this being reused over and over. But let's talk about it when this ransomware does happen. What are some interesting things I've learned about doing response? And one of those things is, as you come across different devices, you'll notice that when they encrypted, that is a touch time. It's a date modified time. And you can use that time to kind of chain the events together to understand how the adversary is moving through the network. A few of them that I responded to, it's not all I ever do, but they were live. The adversary was still there. And I was able to kind of track them back, kick them out, figure out how they got in. That was root cause analysis for me. Another piece of this, and something that's really exciting, and maybe you already know, but if you don't, that because of that requirement to leave the box useful, and this will be talked about here in a second again, I'll show this off, but there's a HTTP error log that isn't part of the Windows logging system that can show things that try to scan the devices. And in this case, if you see that Trinity, it's kind of small there, but if you see Trinity as a GET request, it's actually a signature for Nmap being ran in your network. Same thing goes for, we can use the firewall log on Windows. The local firewall log isn't just in the Windows event log system to understand what network traffic's going on that device also. And if you take care, you can go into the advanced firewall and enable that one, change the size limit for that log, as well as enable it to log for things that are successful as well as failed. And this is the place where you can do that. Often in enterprise is already default. When you do that, you can collect all the information and start to track that internal activity. And this is kind of, this is GraphTool and Elastic that I was able to use on those logs to put all this stuff together and really draw out what access happened, even after the fact. And one last piece, and I'm going to show this off here in a second. Here's a few logs that are really, really helpful for tracking SMB activity and remote desktop activity. And I say this because what has to happen, especially in a live situation, is when ransomware is detonated, the actor then has to disconnect. So yes, the logs were cleared, but as soon as that actor disconnects, there's another log generated. And in this case, that log actually was generated with the IP, with the network address, in this case, the external address that was being used by that actor. And this is where you can find that. And I'll show you here in a second. Also, I made a tool that can put all this stuff together and help you do these incident response capabilities. And we'll look at that also and give you a demo of that right now. All right, for this demo, get with me and here you are. The worst has happened. IronCat strikes back, or insert whatever ransomware of your choice. You jump it onto the box, and the same idea applies. First, just in case you haven't been there, and some may think this is really simple, but none of the links are going to work because they're also encrypted. And the recycle bin is generally unaffected, so you can still get to the file system that way. It's the easier way to get in. I've even done instant response where, like, when I was doing it remote, the Windows R key didn't work correctly or didn't pass through the way I needed it to, so this was the best way for me to get around. Inside the event viewer, you'll find that for the most part, the logs are all gone. This is going to be the case, but in my experience, when ransomware was done by live actors, and sometimes even when it wasn't, the order of operations requires them to disconnect from the session, whether it's SMB or RDP, after the execution of the malware that clears those logs. Now, Hyper-V uses RDP, so I'm going to disconnect from Hyper-V, reconnect to Hyper-V, and then open up the event terminal again, go to Terminal Services under Windows, Local Session Manager. In that location, you can check the logs that are generated from the disconnection of the RDP session, this RDP session that existed prior to the logs being cleared. And right here, with event ID 24, this is where you're going to find the IP address of the connection that existed while the logs were cleared. And this is what you saw in the slides just prior to this. Okay, kind of two key notes there. But one last thing I wanted to show you is, remember the requirement of ransomware from the actor's perspective. They just want to make money. Well, usually speaking, they just want to make money. So ideally, your machine is not bricked. That would be kind of counterproductive, which for the most part means that the System32 folder under Windows is left alone. In here, in the System32 folder, you will find the folder named log files, and inside that folder, another called firewall. Now, this is the best part about these logs. They are not EVTX logs, and they're not part of the Windows event log system. So the log clearing that the actors didn't touch these. Now, if you want to open these up on the box, which I don't recommend, just scrape them off and look at them later. But if you want to open them up on the box, you have to use an administrative notepad. But once you do take a look at these, you get a lovely historical accounting of all of the connections made to this machine. Especially you have the setting to log allow connections as well as drop connections, which oftentimes that I've found inside of an enterprise environment is on by default. And though this mashup of text is lovely in its own right, my main job isn't actually to make malware. I just thought it was interesting. What I actually do is incident response and cyber defense and red team operations that sometimes includes making malware. But I've also created this tooling to process this file. It enriches it with local and external DNS. It uses GeoIP and threat information and aggregates it all from multiple machines into an elastic stack so that it looks like this. So what you're seeing here is the same logs that you saw collected, but from two devices that were involved in a live ransomware incident last year that I responded to. And with the location changed here for the source location to protect the innocent. Those local firewall logs were collected and then provided this map of every connection made externally with country codes, known IPs on threat lists or Tor nodes. So if it's green, there's no threat. If it's red, there would be a threat. It didn't detect anything on a known threat list when I dumped it into this Elastic instance this time. But you also get protocol and path distribution, analysis by firewall action, so you can see like a spike there and drop packets, as well as counts of ICMP type, and really just any way you can split up this information. I'm sure there's a lot more to be done with it. The more devices you collect, the more you can build out the attack paths through the network. In this case, RDP and SMB were the primary means of lateral movement. When you search for 3389, you get a positive internal to internal connection. I say positive because there's a green dot right there on Jacksonville, Florida, which is where I changed the location to. And when you put this into a list inside Discover with the same kind of search and only look at the source and destination IPs, You can see what other devices they were connecting to. And you can do the same for SMB. And this has been an incredibly effective tool for me, and I plan to keep expanding on its capability. Right now, I'm calling the tool Revenant, and you can find it and download it and use it yourself with the GitHub that's associated with this presentation that will be at the end. So that being the case, that I'm showing you how to respond, what can you do to try to prevent this? Well, it's all the things that we already talked about for detection and response, but it's also reducing your attack surface. I've seen RDP as an entry point too many times now to count. We just looked at client-to-client traffic as something that you can monitor and stop the lateral spread of that. You do have time while there's live actors in your network. Monitor file access and write IO, and the same like C2 and log review and all that stuff. But one really key point that I want to focus on is emulation. You have to test it. You have to test what your capabilities are and what you can and can't do. And with that, you need to apply that knowledge right now. So let's talk about next week. You want to go and make sure you have detections in place that allow for antiviruses to fail, and you have behavioral capabilities that are more difficult to bypass, so that what the attacker that you're defending against doesn't just have to change some strings. In the next 3 months, let's talk about these TTPs that we looked at for incident response and develop your tools internally so that you can track this activity once you do find it. And within 6 months, use the resources in this GitHub. And please, absolutely, whether it's the Revenant tool or whether it's the already released malware that you can download yourself to test, like this is safe malware. There's a blog about what it does. You can use this internally to test your environments and run exercises with your team. Thank you so much for joining me at RSA 21, and happy hunting.